Professor Yang Lee, and very happy to be here again at KAIST, and also the KAIST that allowed me this second visit. I would like to talk about the semiample divisor, so the cone also, on the symmetric product. Symmetric product of curve. And this is a joint work with Michele Artebani and Antonio Laface, that are Italian but are actually in Chile now. So Conception University. Okay, and let me start with some introduction. So C will be a smooth, projective curve over C, and C2 will be the symmetric product. So we take where the equivalence is given by the usual involution. It turns out that this is a surface, smooth surface, and the map from C cross C to C2 is ramified along the diagonal. And I use the notation, the usual notation, that a point is written with the point of C2, with the divisor notation. And usually I take the genus bigger than 2, and in that way it turns out that the variety C2 is completely determinate and determines the curve C. So it's clear in one sense. Also in the other sense, it's a sort of a small Torelli theorem. You can construct. And so never. For instance, in C2, we have many embedding on the curve C. You fix a point P, and then it's just the curve CP given by X in C. Okay, these are called the coordinate curves, and they're isomorphic to the curve C. And although there is this more or less equivalence between the two, it's not easy, not clear how to recover, to understand. The geometry of C2 from the geometry of C. And so I'd like to start with some problem. So problem 1, which is the most famous, is what about the ample cone of C2? This is not known, and one remark that if you take the Néron-Severi of C2, so the divisor mod out the algebraic equivalence, there's no torsion in this case, so is equal to the usual numerical equivalence. Then it is Néron-Severi of C2 is isomorphic to Z plus the Néron-Severi of the Jacobian of C. Record that the Jacobian of C by definition is peak 0 of C. And the Néron-Severi of the Jacobian of C is isomorphic to the endomorphism of the Jacobian of C fixed by the Rosati involution. And the Rosati involution is given by, in our case, by the involution I. So you have the Néron-Severi of the C by C, which is essentially the endomorphism of the Jacobian cut down by two classes to the trivial classes, and the Rosati involution is nothing than this one. And this is when you tensorize by Q, it could be a difficult algebra, so it could be difficult to understand. And in fact, this kind of groups in general can reflect some arithmetic of the curve C. But now take C general. When C is general, so the endomorphism is Z, so the Néron-Severi of C2 is just Z by Z generated by the class of the coordinate curve and alpha of the diagonal. I call just C, maybe not. C, which is the class of CP. CP is ample because this coordinate curve CP are smooth and CP square is equal to 1. So they are ample curve. And that this diagonal is x plus x. And this is divided by 2 because the map from C cross C to C2 ramify along the diagonal. Okay, so this is not effective, but 2 times is effective. And so it's just something like this. But also here the ample cone is not known. So one other condition. Take a class like this. So I just write a general combination, but I take minus delta here. This is ample. If this is ample, so alpha and S you can take in Q or something like this. This is ample. Then it turns out that S must be bigger or equal than the square root of G. In fact, if you put square root of G plus 1 C minus delta and you take square, this becomes 0. And if you take something less than this, this is less than 0. And the converse is the Kovidakis conjecture. That is more or less equivalent, more or less, to the Nagata conjecture by the same kind of. And but Kovidakis prove the conjecture. If I see the result, when the square root of G is G is a square I write down k minus 1 because I will use this notation later. So when this is square, then it's proven. And I'll be back in a few moments to the proof of Kovidakis conjecture. But I would like to say that also in this case, we will consider exactly this case. Although this case is the Kovidakis conjecture is known, but let me give now problem 2. What about the effective cone? Okay, C general. What about effective cone? Maybe take G square. And then, okay? And in fact, let me go back to the proof of the Kovidakis. Proof. The Kovidakis proof is given by constructing a curve in what it is the extreme array class. So K is K C minus delta, the class, in the following way. So you take a map, take a curve C that maps on P1 of degree K, K to 1. So in fact you can construct a curve in this class using this map. We use K, which is the K that we need, but you can construct in the following way. And then you construct gamma of F. You take the point, so the symmetric graph, such that f of x is equal to f of y. Then you subtract the diagonal and then you close up. So, or you subtract the diagonal in the sense of the divisor. Okay? So, okay. In this way, you prove easily that this class is this. Okay, C minus delta. If also C, if the ramification are simple, it's not so necessary for the proof. So it means z to z squared, so it's something like then also this curve is smooth, and so is irreducible. So that this becomes a Neff class because it's smooth, so it's irreducible. Then when you add something with epsilon, well, I forgot a condition here. Obviously, alpha must be bigger than 0. So when you add epsilon positive, so this is ample, and this is Neff, and so this becomes ample. And this exactly that the slope between this part and this part increase. But let's consider the case when G equal to 4. Well, in G equal to 4, in fact, C general, so there is a trigonal curve in this case. And moreover, there are two maps. Of degree 3. In fact, you take the canonical embedding, it's called K, canonical embedding, And the image is in a quadric, a smooth quadric. And then this is P1 by P1. Is a 3-3 curve. That means that when you project in the two P1, we have F1. So F1 is just composing K with P1 with the first projection, and F2 is with the second projection. So we have these two maps, and then we can construct, and we can do like that. Also, generically, the ramifications are 2 to 1, and we are done. But when we take now the genus square, but bigger than 4, so 9, 16, and so on, the general curve is not k-gonal. For instance, when the genus of C is 9, is by Brunner or by computation, is 6-gonal, not 4-gonal. So you have not this curve in the general. And the proof of Koubidakis proof uses the openness condition of the ample cone. The fact that ample is open condition, is an open condition. By deformation. So we don't know, not clear, we don't know, problem 2 prime, say, if the class KC minus delta is effective. So when C is general. And the remark, n should be bigger than 1, because n equal to 1 essentially gives the k-gonal condition by the theory of the correspondence. So this is quite and the problem is interesting because you face the problem to construct curve in the symmetric product. So you know that this is extreme array, and it's more difficult to construct curve in the symmetric product, well, with a nice condition, than in the standard product. For instance, it's more difficult to use this linear system with more a GK2 or GK3, because to make this symmetric, usually, for instance, the GK2, you can take the tangential correspondence from a point. If you have a curve, plane curve, you have a point, and then you take the other point that intersect the curve point and the other point, and you construct a curve in C cross C. But this is not symmetric because there's no bitangent. It's not general, it's not bitangent. So problem 3 that I would like to talk about, I'd like to talk about semiample. divisor. Here we can say something, and we started to consider the case of genus 4 when we have these two map, and we generalize. So starting from the genus, so it is completely open, the ample condition in this case, obviously, because the genus 4 case. So we realize that can be generalized from, for generalize, we can to curves of type KK in a quadric, in a smooth quadric. Also the non-smooth case can be considered, but it does not, never becomes semiample, give semiample divisor. Smooth quadric. So we take if you like, you can embed in P3, and we take the curve C. We take FK definition. We consider the family of FK of the curve C in Q of type smooth, of type KK. That means that C is a complete intersection of Q and XK, where XK is a surface of degree K, and we take smooth. So it is FK. FK is an open is an open set in the projectivization of KK, of the quadric. Now it is clear. It's open. The dimension of K, I hope not to make a mistake, it should be K squared plus 2K. The genus of C is K minus 1 square. And now we have these classes. We have two classes from the curve C. We have two map, F1 and F2 on P1 by taking the projection. And we have gamma 1 and gamma 2 inside the symmetric product C2 with the class as numerically KC minus delta, and so they are also numerically equivalent, and then this becomes 0 because we are exactly in the Kouvidakis extremal ray. And so the question is, so we know that so we have these classes, and when we take S bigger than this K, this becomes ample, and we would like also we know that this class is effective, and we would like to know if this is semi-ample. So we have the result. Also, just to give the notation, let's call L1 F1 star of O1. So the pullback of the O1 here, the line bundle gives this map, and L2 F2 star of O2. So we have two G1K that correspond to the two rulings of the, and this is the line bundle notation. And so now we have the following proposition, not so difficult, but proposition. So gamma I is semi-ample if the difference is torsion, is a torsion. This is in peak 0 because they are numerically equivalent and there is no distortion. In peak 0 of C2 is if and only if OC of L1 let's say is torsion in peak 0 of C, and these two are equivalent, are isomorphic because they are the same Albanese variety and also they are principal polarized, and so they are on the same peak 0. So this is the condition to be semi-ample is reduced to the curve in this case, and the difference of the two, so the difference of the GK1 minus the other one, so you take K point in the first curve, in the first ruling, and K point in the other ruling. You take the difference and you have something in peak 0. So first ruling is Q1 QK, second ruling second, and this should be torsion. It's the same, okay? And if this happens, also if call this maybe LC, just the difference of the two rulings. If LC n is equal to OC, then n it should be bigger or equal than K. For the not trivial, not till K it cannot be. Okay. This is the result, and the consequence of this result is the following. Now I'll be back to the proof. Consequence let me first give a definition. We consider the canonical ring. Maybe it's not a good name. Canonical, maybe standard ring. I don't. Let me say the. Let's call the canonical ring. It's not the. The ring of the canonical. The ring of canonical divisor. So we would like to pass from the numerical equivalence to the linear equivalence. So there are not many canonically rationally defined on the moduli setting of divisor in the symmetric product. There are essentially two of them, k and the diagonal, or also alpha of the diagonal. And so we take the ring generated by k a plus b delta, and now we can construct a sort of restricted Cox ring canonical divisor or delta alpha, if you like. Call this A and B are in Z, and then A is finitely generated if for the curve as before, if here is for if C belongs to Fk, obviously. If LC is torsion. So let me give, maybe I give some of the, a piece of the proof of the first one, proposition, proof of proposition, just one piece. Maybe I prove that if this is torsion, well, these and these corresponds to these isomorphisms. You have to do some computation, but is more or less clear by the when you know this isomorphism. This becomes this divisor goes to this divisor under this map. So if this is torsion, we would like to prove that if O of gamma 1 minus gamma 2 is torsion, then gamma 1 and gamma 2 are semiample. The converse is also easy. It's more or less clear. Why? Because n, it means that n gamma 1 becomes linearly equivalent of n gamma 2, because this becomes trivial. Now you can remark also that gamma 1 by gamma 2 is as intersection 0, and this also implies, well, we can remark also that gamma 1 set theoretically intersect gamma 2 is empty, because otherwise there should be a component. Otherwise they have a component, a common component. But in that case, it means that there is a point x and y which belongs in gamma 1 intersecting gamma 2, let's say with x different from y. But if you remember, the construction of gamma 1 are the point x and y such that they are in the same fiber, but then they should be in the same in the second ruling. It is impossible because the rulings are distinct. And so you see that you have a map on P1. You have to prove, well, you can prove that in fact everything, the map is cannot go to C2, cannot go to a curve from C2 after the Stein factorization of your map. You can go to B, but then this B is in fact P1. It's easy. So the fibers are connected. This is like this, and we see that becomes semi-ample because a multiple of this generates your stuff. Okay. To get this theorem, we need first. So we need some remark first that a multiple. So gamma 1 plus gamma 2 is also semi-ample, and the multiple of these, I think, I'm not completely sure. So don't. I think it's 2k plus 4, but now I take a multiple of gamma 1 plus gamma 2 is a canonical divisor, is in the ring of canonical divisor. This is take a multiple, and so is a multiple. It means that is linearly equivalent to a k plus b delta. First, so we find one semi-ample divisor here. There is another one semi-ample divisor. This is one. Second, there is another one. This is the orthogonal to the diagonal. It should be also here. Please don't completely believe in me, but it should be like this. I can do the computation, but this is the one that with the diagonal is 0. Let me remark that I didn't say that the canonical, numerically I didn't say, just remark. The canonical is something like, no, it's something is 2g minus 2c numerically minus delta. Okay, from the map 2 to 1 or whatever, it's like this. And then you compute easily what are a and b that make this 0. And that this is big enough. You can prove in various ways, but maybe without do the computation, you can use Kawamata Vivek or something like this, but without using the computation, we have the map from C cross C to the Jacobian, let's say, which is peak 0, by the difference map. Maybe I take C non-hyperelliptic, and it is not hyperelliptic, it contracts just the diagonal. The diagonal is contracted. Then here we have C2 and our mapping, called P. And here we have -1 map, L in L -1, and the quotient is the Kummer. And then the symmetric product goes to the Kummer and contracts the diagonal. And then you can embed the Kummer, or you can send the Jacobian by 2 theta. It is embed the Kummer in some Pn. Anyway, it is a projective variety. And then you have a map from C2 on Pn that contracts the diagonal. So the orthogonal becomes big Neff and semi-ample. Then by standard argument of the Cox ring, when we take A, well, the sub ring A prime generated by this multiple and this class, because they are semi-ample, is finitely generated. And then if we add delta, which is the only delta is out of this because it's not ample. It's not. I mean, if you take the convex combination, positive combination of these two, we are in the ample cone. But delta is out. But if we add delta as a generator, so 1, 2, and 3 generator, we have A. And so this becomes finitely generated because, you know, we take the standard. So, but what about example? Because example. Also, we have the following, let's say. First, we have a very good example. But since I have not much time, I put in all in a theorem too. First, first let me give you a definition. I call Fk torsion. I would like to give a little more space to definition. So we call Fk torsion a subset of Fk such that L of C is torsion. And maybe I call Fkn the subset of Fk torsion such that Lc n is equal to OC and the n torsion. Okay, so the theorem is like this. Fk k is not empty of dimension for k plus 1. The important fact is that this codimension of Fkk in Fk is G. Second, Fk torsion in Fk is analytically dense. So the structure of this kind of set is similar to the Néron-Severi, for instance, of K3, when you have more than, for the Néron-Severi, the Picard group is bigger, has rank bigger than 1, or in the surface in P3, when the Néron-Severi is bigger than 1, something of density. So the general is not, but some of them are that way. And there are a countable number of components. So the first first part is in fact the example, but there are other little examples. But this is called the grid curve. We call this grid curves. So we take k lines on P1. P1 by P1. We are in P1 by P1. So we take k lines in the first rolling. K lines. Distinct. And we take k lines in the other. So L1, L2, Lk, M1, M2. Now let's go from below to M1, M2, Mk. So we have these points which are, if this is Mi and this is Li, the point Pij, something like this. And we would like to take the curve that passing through this point. Take C in Fk, we call C a grid curve if C belongs to Fk and C contains Pij, something like, I don't know. In fact, let me say that I would like to, I discussed with my colleague and I would like to call this curve, I mean, this was a construction of my colleague, I must say, very nice construction, simple, but I would like to call this grid curve, but they are more conservative because it seems that you have something that you are doing grill, but they are more conservative than me, so they call grid. And then, okay, you take this curve, and then you notice that when you take L, if you take Li intersecting to C, and then you sum out, this is obviously it is the sum of this Pij, but in the same happens if I take the sum of Mi is the same. And so, but L intersecting to C, this is just n times L1 restricted to C, and this one is I call M, but this is n times L2 restricted to C. So no, this is O1 restricted to C, O1 restricted to C, in that way. So it's n times. So it means that n L1 minus L2 to n is trivial to C. Because they cancel, exactly. No? This is OC. Okay, now you study this kind of curve, and then the equation in, it's not so difficult, the equation of this curve in coordinates, say Z0, Z1, W0, W1 is something like F1, Z0, Z1, G1 of V0, V1 minus F2, G0, Z1, G2, G0, W0, W1 equal to 0. Because n lines in that way, for instance, these and these give n lines and then you see that not only they are in a one grillet curve, but they are in a lot of this curve, and then you prove by some analysis that by this equation that this is a dimension this, and then the general is smooth, and you can prove also by Bertini theorem that the general is smooth. Okay, so we obtain a good component. How to get the general? Well, the general For the general, it's a little different argument, but we use the first construction because I am lazy, a lot lazy. So we take Fk. Over Fk we have the universal. So remember that Fk is contained in some OP, in the equation OP1 by P1 kk. So it's a set of equation. So we have the universal family. Yes, we are containing some Pn. So it is which is the Hilbert scheme of this linear system on the curve. This is universal curve. Then we have the Jacobian. And then we have a section of this Jacobian given by, we call this the point, on the point C we have the curve C here, and on the point C here we have L of C, which is the difference of the two G1K. This is in peak 0 of C. So this gives a section. This is called in the language of Griffiths a normal function. It is a normal function. Now I am more confident, although maybe it is more difficult, but depend difficulty what you're more used. It is a normal function. And Griffiths also give a way to study how this normal function behave with respect to the constant function. But now, for instance, the torsion are considered constant function. Now I explain better. So we can take now U simply connected inside Fk. Open set. And so we can trivialize in a C-infinity way, also in the analytic, but real analytic way, for instance, this family. So over this family, we have the Jacobian restricted to U, and then we have a trivialization. You take a point 0 here with the curve C0, say maybe. This goes to J of C0 by U. So it is a family of torus, but when you look from the point of view of just the real topology, this is just V2G, Z2G by U. And then you see that you put all the CG, it's just you take CG mod some lattice and you put in, taking a basis of lambda, you put this in R2G divided by Z2G, so like this. And the torsion point go to the torsion point. And the constant function are the functions that are constant to this level. But for what we need, we can project now in the torus and consider the map from U to this torus, T0. Call this project, this trivialization, maybe I call this tau, T. And this is just, first you take our normal function, and then we take tau, and then we project in the torus. No. First the normal function, then with the trivialization, and then the projection. And we would like to show, for instance, if we can show that this map is if we can show that the map is open, so for instance, if the differential of all this stuff is submersive, we have the immediate density, because the torsion point here are the torsion point, which are dense. Okay, so, but computer differential is a little hard. Well, we did in for the genus 4 case, I must say. But yeah, I'm sure with some work it can be done also in that case, for instance, along the grid curve. But there is a device that I learned from Mark Green. I'm finishing in 2 minutes. Is the following. One, although it seems strange, but if you follow the trivialization, it turns out that the fiber of C, of the final map from U to this, C, are complex analytic. Although the map is only real analytic, so it's something like that the fiber are parameterizing by something which is real, is not complex. But they are analytic, one by one. As the torsion, in the case of the torsion, it is clear, because it means that this line bundle, n times this line bundle, becomes trivial. And then we have a fiber with the right dimension, the grid. Then maybe there is, we don't know the differential, so it could be reduced, but is at the right dimension. So we can take something, a section, something complementary dimension variety, complex variety, that intersect in locally in just one point. But then the well, I'm cheating a little, so it's not, but more or less, what happens is that this intersection between two analytic subvariety is one point. You can prove by residue theorem, which is this is something locally positive. So you have two subvariety, analytic subvariety, and this is some positivity condition that you can compute, taking the sphere around and compute the residue, like the positivity when you intersect two algebraic variety. And then when you move a little your fiber, well, I have to be a little careful, because we have to take some other bigger fiber. But anyway, when you move this fiber, this intersection must stay, because this is an homological property of the positivity of this intersection. And so, okay, also the other fiber must intersect this something like this, and then it is open. So that when you have something which is, you have something which is parameterized also continuously parameterized family of analytic subvariety. These are the fiber, then the map is contains an open, and then the differential is generically surjective by Sarr lemma. So, I mean, you have the fiber like this, and you prove that something transverse must hit all of them, and so you have to find this. No, I didn't explain very well. We have to enlarge a little this variety, look at this, and then intersect. Anyway, using this argument, we prove that this is dense, and I think I stop.